In the first part, we saw how we can use these 315 and 433 MHz RF transmitter and receiver pairs and how we can make an antenna for them. Now in this second part of the series, we will see how we can add addressing to our system and increase the number of switches we can operate wirelessly. So let's get started. The first thing we have to see is what is addressing and how we will use it in our system. So for example, we will see a 4-bit addressing system. That means the address will be selected by 4 bits. That means a total of 16 possible addresses. Now, if we see the 4 bits themselves, they are represented in ones and zeros. Therefore, they are binary. We have to select the address of our system ourselves, like I have selected over here 1001, and this address should be put same on the transmitter and the receiver. Then only they will sync up and work together. What this MSB means is that in our system, we send this most significant bit first. Now these 4 bits can either be sent first while transmitting, then the data can be sent, or the address can be sent after the data has been sent. In our case, address will be sent first. So what will happen is these 4 address bits which we will set will be sent by the transmitter each time it wants to send any data through the transmitter module. Now about the receiver. The receiver will first receive any data that is being transmitted in its range, that includes any data from other transmitters or transmitters not used in our system. As we transmit the address bits first, the receiver will store the first 4 bits and read it. And if it matches to the address we have given to the system, then only it will pass the rest of the data through the rest of our circuit. But if the address doesn't matches, it does nothing. Now after we have learned about the addressing system, we can take a look at these two ICs, the ST12E and the ST12D. We will use the ST12E for the transmitter side and the E stands for encoder. We will use the ST12D for the receiver side and the D stands for decoder. The ST12E IC includes the addressing system which is of 8 bits instead of 4 bits which we saw, and it also generates the output signal which can be transmitted through the TX module, which will be then received at the receiver module, and the signal will be sent to the ST12D IC which will check the address and also execute the data which will be received along with the address. Now let's take a look at the pinout and circuit diagram for the ST12E IC for the transmitter. As we can see, pins 1 to 8 are the address pins which will set the 8-bit address for the system. For this system, I grounded all the address pins to put 8 zeros on the address. Pin 9 is ground for the IC. Pins 10 to 13 are the data pins which will be used to connect 4 switches to control 4 outputs for our remote control system. The switches will be connected to ground. The TE is the transmission enable pin which is active low. That means when it is connected to ground, the transmission will be enabled. Pin number 16 and 15 are for the oscillator frequency across which we connect a resistor to set the oscillator frequency at which the IC will operate. Then the 17th pin is D-out pin which will be connected to our TX module. Pin number 18 is VCC for the IC. We will use the value of 1 mega ohm for the oscillator resistor. Now onto the receiver side. The pins of the ST12D are kind of similar, like the address pins are from 1st to the 8th pin which we will connect to ground along with the IC ground pin to match the address of the transmitter. The 18th pin is the VCC for the IC. The 17th pin is a little different. It's used to connect a LED which will show the status of the connection between our transmitter and receiver. Then there is an resistor connected between the 15th and 16th pins which are for the oscillator, and the value we use for the ST12D is about 100 kilo ohms. As to why did we select the value so different from the transmitter, we will see that further in the video. The 14th pin is the D-in pin which will receive the data from the RX module. Pins 13 to 10 are the data lines and can be controlled via the switches on the transmitter. So for testing, we will attach LEDs with current limiting resistors. And here is the circuit completely built up on breadboard. As you can see, there is the ST12E IC with the address pins grounded except the 5th pin, which is connected to VCC to set the address as 4 zeros, 1 1 and 3 zeros. Then there is the oscillator resistor of 1 mega ohm connected. Then the transmission enable pin is tied to ground. The data out pin is connected to the TX module's data pin, and the TX module is powered through the VCC and ground pins connected to the VCC rail and ground rail. I have used this 4 DIB package switches for controlling the data. Now let's see the receiver side. The RX module is connected and powered through the VCC and ground pins. The data pin is connected to the data in pin of the ST12D IC. There is the LED for checking the status of the connection. Then there are the 4 LEDs and current limiting resistors connected to the data output pins of the IC. There is the oscillator resistor of 100K. Then the address pins are connected to ground and VCC, similarly to the transmitter to match the address. Now after I power it up, we can see the connection status LED is lit up. That means the transmitter is successfully connected to the receiver and we have not messed up the wiring. So that's a good sign. Now these are 2 separate breadboards and I am just connecting them together for powering them with a single supply, and no data wires are connected between them. Now if we slide the switch on the transmitter side, we can see the LED turning on at the receiver side. Similarly, we can switch all 4 LEDs wirelessly, and we have successfully created an address based 4-bit wireless control system. We can use it to control RC cars or to control lights, fans or switches by adding relays. Stay tuned for an upcoming project video where we will make this project on a PCB and install it in our home or room and automate the lighting, fan control, etc. Now the ST12E works at about 3.6 kHz because of our selection of the oscillator resistor, and ST12D works at about 90 kHz due to our selection of the receiver resistor. There is such a difference in operating speed due to the architectural design of these ICs, where the manufacturer has stated in the datasheet the operating speed of ST12D, that means the decoder, should be 50 times more than the operating speed of ST12E. And if we power up the circuit and check the frequency with a multimeter, we can see the ST12E is operating at about 3.6 kHz and the ST12D is operating at about 90 kHz. This frequency measurement is important because by using it we can troubleshoot various issues in our system, but that is a topic for another video. Now as you can see, I have applied 2 different sources to the circuits to simulate more or less the wireless controlling of the circuit, and as we can see, it works right. So if you found this video useful, then do check out my other videos. There will be more videos on this series soon, so stay tuned for that, and subscribe to the channel if you haven't and press the notifications bell so you won't miss any upload. And if you liked this video, then do like, share and comment your questions. Thanks for watching.